So one of the challenges is, of course, that there are certain situations where global and non-local interactions are very important, but incorporating them into force fields is also expensive because there's a parametric growth of model complexity, and it's exponential. And managing this growth is very hard because you don't want to introduce any uncontrolled or potentially uncontrolled approximations that could deteriorate the quality of the prediction. And so usually dealing with complexity, and this has been a theme throughout this workshop, usually dealing with complexity is done by introducing symmetries and symmetries, and usually it's physical symmetries that we impose in order to simplify the problem, right? So those symmetries, they introduce regularity and then thereby simplify the parametric complexity. And since this is mostly like a physics, it's a physics problem, this is why people deal with this reconstruction problem as in terms of a physics problem. And that means that the symmetries that they impose, they're mostly the physical symmetries that we already know from the Hamiltonian, for example. And then, of course, they're very effective. We put them into our machine learning models, and then we treat the reconstruction as a physics problem. But it's really not just a physics problem. It's also an empirical problem. So we heavily rely on data. And this empiricism of the reconstruction problem gives us the chance to also incorporate other symmetries that really are not physical, they just come from the data. And this is what I want to focus on today. So looking at the numerics of the problem and then try to introduce simplifications that increase the accuracy and or the performance of those models. Okay, so this is about force field reconstruction. So obviously different fields of atomistic modeling, some of those methods also apply there, but I will focus on force field reconstruction here. And as Frank already said on Monday, this is a problem that is particularly conducive to the machine learning treatment, and mostly because it's a supervised problem, and we need to learn a very simple mapping between geometries and energy and force labels. And this can be done, so getting started in this field is very easy. This can be done in very simple ways, and the good thing is you always get an answer, right? So even if you have a very simple model, you will get an answer. It might not be good, but it will be an answer, and then you can use this model for example, in MB simulations and see what you get out. But then as you develop your solution, you can look at the unique properties of this problem and then try to make your model better, right? So for example, one of those unique challenges in this application is that we are learning on sets, right? Because atoms are indistinguishable, and so that's something that is that in traditional machine learning applications doesn't appear very often. Then there's several invariances and equivariances that the labels present. So energy and forces, they have certain properties that we ideally would like to incorporate as well. And there's one extremely unique property about this field, which is that we have very stringent speed and accuracy requirements. This is usually not the case in many other machine learning fields. And here we have to be, on the one hand, we're competing on the low accuracy but high speed, and we're competing with traditional classical force fields, which only use mechanical approximation, mechanical like functional forms to model atomic interactions. They are extremely fast, not as accurate as first principles calculations, and they are on the other extreme where we have fairly expensive calculations, but of course they are very accurate. So machine learning sits in between, and we need to trade off both speed and accuracy to make it worthwhile, right? Okay, so before I get started, I would like to propose a little historical perspective on how the field of atomistic modeling or force field reconstruction in particular developed. And of course, this is just, it's a very simplified historical view. It's one of many, but bear with me here. So it all began around 2010, when people started to see the appeal of using machine learning models for this application. And back then, they used very, very simple models, so mostly linear models or very simple MLPs back then. And the focus very much was on feature engineering. So people tried to find good descriptors that incorporate some of the properties or featureize some of the properties of the input, and then use those descriptors in simple models to get good predictions. And this list of examples is not comprehensive at all. This is just, those are some models that I'm particularly familiar with, but obviously there's much more. And back then, those models, they were very general models. They started from generic hypothesis spaces, and they were very much black box models. But the descriptors, they carried much of the expressive power. But the problem is there's no systematic way of designing descriptors, right? So you cannot. It's mostly trial and error, and eventually you will hit a barrier. And then a few years later, people started to look at more complex, deep architectures, and like one key moment was when convolutional neural networks started to be applied to graphs. So they have been generalized, for example, using message passing to graph structures, and now the idea of convolution could be applied to other to complex topologies like graphs. And again, we were back at we still remained with models that were fairly black box and started from generic assumptions, but this was an interesting time because there was this idea that you can just if you put enough data and put the right data in the model, then the model would through very generic principles of convolution and learning convolution filters somehow figure out how to find good representations for the atoms and then let those atoms interact. And this is a very powerful idea, and a lot of success has been made during this time. And sometimes it looked like magic because how effective everything was, and this inspired many people, and the field grew very quickly until a few years later. Again, people started to realize that it might be indistinguishable from magic, but they still wanted to trust the models, and this is when they really developed those networks even further into well, they looked at the architectures. How can we improve them? How can we incorporate physics? And some of those examples, for example, are the incorporation of directional features using sophisticated parameterizations for those convolution filters using circular harmonics, for example, or this whole field of geometric deep learning emerged at the same time, where people tried to incorporate certain like group invariances into those models. And so this architecture engineering phase turned out to be this was a very, well, the great strides were made towards getting better force fields in this area. But then all of those examples, all the way back to 2010, all of those examples will be focused on somehow exploiting physics and putting physics into those models. So there's still, from the if you take the empirical or the statistical view on this problem, there's many more things that can be exploited, and this is what I want to talk about today. And some of those, so some structure within those models is really just created by, for example, correlations in the data, or we heard several talks about incorporating differential constraints into those models, and those differential constraints, they also impose some structure that can be, in some cases, exploited to make those models easier to evaluate and train. And so those performance improvements can then be used, for example, to remove those uncontrolled approximations that I talked about in the beginning, where for example, locality assumptions that are now pervasive in many force field models. Okay, so this whole looking at the numerics was motivated by the fact that quantum interactions are global, in fact, and many models, they in order to simplify the parametric complexity, they adopt a localization assumption, which is very reasonable. So you could, if I would steelman the case for localization assumptions, I would say, well, since interactions decay exponentially with distance, it makes very much sense to only look at local interactions. And then on the other hand, like this would also create like fragments, for example, fragments that can be reused. So this helps with generalizability and so on. But then we heard several examples. So for example, in this talk by Raphael, we heard that although those global interactions only have a very small scale, so they would not necessarily show up in energy and force errors. If you look at those as a performance metric for those models, they might have very significant influence when those models are applied in, for example, in the molecular dynamics simulations. So completely ignoring global interactions can be a problem. So we set out to reconstruct global force fields that don't have this locality restriction. And this is very much a problem that has been also identified by other people. And this is an emerging field without a good universal solution yet. So mostly the approach is to take well-established local models and then combine them with a global correction. But obviously this decomposition, it's unclear how to really model this decomposition, because interaction scales cannot be decomposed like that. So one way to overcome or to not have to face the challenge of doing a proper decomposition is to create a global model that really takes everything, all the interactions that are in the data, and tries to represent them within one model without doing this decomposition. Okay, so just to give a little outline for this talk, people have been incorporating physical symmetries and conservation laws into models to make them more efficient. Obviously, the idea behind or the motivation for this is that if all atoms interact, this creates an exponential state space, and this exponential state space is hard to manage, except for if we only look at physically feasible configurations, and then it becomes very well manageable. So today I want to focus on correlations in the data itself that also yield structures and patterns that can be exploited. Then another instance of our data-driven interactions. So this is, so for example, if atoms interact if there are physical interactions between atoms, it's not necessarily the case that within the machine learning model, those physical interactions are as relevant as they are in physics. Because, so for example, if you have two atoms interacting, they might not be, if all of the data points in your data set interact in the same way, they might not have the same importance from the statistical point of view as they have from the physical point of view, right? So it's very important, I think, to look at interactions that really emerge from the data, and in addition to the interactions that are really due to the physics. So those are all statistical symmetries that can be exploited. And then lastly, there's some architectural patterns that can also be used to improve the models, and mostly those patterns are due to, the example I will show today is if you incorporate differential constraints, the models become very big, and this growth of complexity of the models can be managed with automatic differentiation techniques. Okay, so I'll go slightly out of order here to group those three topics in a more logical way. So let me start with this one. So if you approach the problem of modeling global interactions, the simplest thing you can do is just to allow pairwise interactions. So pairwise interactions can be represented by a matrix, right? So you would take all of your atoms or your data points, and then let them interact in a pairwise manner. So you would have a big correlation matrix, and this correlation matrix is the simplest thing you can do, but it still grows very quickly, so it becomes very quickly hard to manage. Even for a few hundred atoms, the correlation matrix will be very large. But even though this is a very simple approach to global interaction modeling, we can take this correlation matrix and then use it in a linear model like kernel ridge regression, for example, or a Gaussian process. And then, surprisingly or somewhat interestingly, those linear models, they already have all of those interesting properties that we now know from much more complex models. For example, we have individual parameters for each interaction, so this gives us directional features. We can incorporate the invariances and equivariances of the labels, so the invariant properties of the energy. Then by training those models on the derivative of the model and then matching this derivative to the forces, we can actually incorporate, we obtain equivariance due to the linearity of the derivative operator. So this linear formulation of the problem already is surprisingly expressive. Now, obviously, an important ingredient to global force field modeling is the data itself. So if we have a model that localizes, we can often get away with fragments, as Alex, for example, showed in one of his examples. But for a global model, we need also global data points, right? So we need to generate reference data sets for the whole system. And one thing that was kind of surprising to me was that this is not really the bottleneck, right? The bottleneck is the finding a manageable global model. It's not really finding the data. So DFT scales well enough into those size regimes of a few hundred atoms, and we can use DFT to generate enough reference data for our models. Okay, so just to clarify again, so if we construct a Gaussian process for a global model, then you would have a huge correlation matrix that correlates all of the degrees of freedom within the molecule, and then also correlates all the molecules between themselves. So this creates a huge matrix that defines the model, and it's very hard to manage. But the advantage is, again, we have global interactions, and so this is one example where this becomes important. So in this particular example, the orbitals located at the two rotors at the end of the system, they overlap, which means that if we rotate this one part of the molecule, we have so all of the atoms contribute. They all interact non-locally, and then a global model would be able to represent this interaction, versus a local model who introduces a cutoff would have to would not see this interaction. And then, of course, for example, message passing networks, they do allow interaction between those cutoff regions, but they're usually very low dimensional. And then especially if they have to traverse multiple hops to make a connection, there's this known problem of information diffusion, which then reduces the expositivity. So through local cutoffs, it's very hard to represent global interactions. Okay, so but let's entertain this idea of using all of the degrees, correlating all of the degrees of freedom in a local, in a linear model. So traditionally, how you would train a Gaussian process is by solving this linear equation, and it's an inversion. Well, you have to invert a matrix or solve.
Using a Gaussian process. What do you mean by Gaussian process in this case? Is it actual GP or?
Yeah, it's an actual GP. So it's a linear model wrapped into a quadratic loss function, and then this is the derivative of the.
I mean, it's a non-parametric process with.
Yeah, non-parametric.
Okay.
Yeah.
Yeah. Good. Okay.
Yeah. So every data point increases the parametric complexity. Yeah. So the obvious problem here is, how you would solve this problem is by exploiting the properties of the matrix, which in this case it's a symmetric matrix that is positive semi-definite. So we can use a slightly more efficient algorithm to do this, to solve this linear system, which is then what we would be able to use for a general problem. So we use the Cholesky decomposition, for example, to factorize the matrix. And then the problem is there's a fundamental time and cost, like time and memory complexity associated with this types of problems, and even an efficient algorithm that solves this problem in a closed form cannot escape the quadratic memory complexity and the cubic time complexity. So the obvious alternative to this is to just train it like a neural network, right? So instead of solving it in closed form, we would just follow the gradient until we find a parameter set that is optimal, right? So the gradient of this very simple linear model, right? It looks like this. We can just follow it until we find a good parameter set, and there's a learning rate that we can set. So this is very much like any neural network is being trained today. The big challenge here is that, the efficiency here actually comes from the fact that we only have to evaluate this matrix vector product with the kernel, with this big kernel that is hard to represent. But if we restrict ourselves to only representing multiplications with a vector, then this can be done without incurring this huge memory cost. Now the problem is that this multiplication is very sensitive to the conditioning number of this kernel, which is notoriously bad because it's a huge correlation matrix, which means that this iteration essentially will be just a random number generator. It will, for very big matrices, not converge at all. So you can be a bit more, or you can try to be more efficient by exploiting the properties of this kernel. Again, you can, instead of randomly walking towards along the gradient, you can say, well, you can compute an optimal learning rate at each step, and then also you can make sure that you don't walk into correlated dimension, right? So you choose orthogonal search directions, and effectively this boils down to decomposition in terms of rank 1 matrices of rank 1 updates of the kernel matrix, which means that with perfect arithmetic you can. It's an iterative algorithm, but it converges in n steps, right? So it's really a closed form solution as well. Now, the big caveat here is that those search directions, you cannot store all of them, because storing them would incur the same cost as the original problem. So you have to find a way to ensure their orthogonality without looking at all of the past search directions. So usually this expression is being written a little differently in a way that only depends on the last search direction. But again, this is numerically very unstable, and in practical cases, although this is all textbook stuff, obviously in the practical application, this would not converge, and in the worst case, just give you a random number generator. So this is all due to the ill conditioning of the kernel matrix, and this ill conditioning the condition number is defined as the ratio between the highest and lowest eigenvalue. And so correlation matrices are notorious for having this exponential decay. So in order to improve the conditioning, what we could do is somehow remove this dominant part of this eigenvalue spectrum. So before we do that, it's good to have an intuition for what it actually represents, what it means, in order to be able to really project this out efficiently. And if we do an eigendecomposition of a typical kernel matrix, then we see that the dominant eigenvalues, they really contain very repetitive patterns, so prototypical substructures of the molecule. And now we can use this information to design a good preconditioner in order to project those problematic dimensions out of the kernel. So the general approach remains. So we try to decompose the kernel into rung 1 updates, but we will now do it in 2 steps. The first step is this preconditioning step, where we actually use a numerically more stable closed form solution to project out the dominant part of the spectrum, and then this gives us the remainder of the kernel, which we then solve as originally planned with the conjugate gradient descent algorithm, but now it will be better conditioned and hopefully converge. Now, interestingly, we can, by managing, so we can either compute, we can compute a strong preconditioner, which is expensive and costs a lot of memory as well, because we use a closed form solution for this, or we can use a very small one and iterate more. And interestingly, there's a sweet spot where for this type of problem with this exponential decay in the spectrum, there's a sweet spot where we can actually outperform the closed form solver both in runtime and memory. So that's quite interesting. Now, the obvious next question is how do we implement this preconditioner? And there's like 3 major approaches here that we could take. The first of which is it's called the Nystrom approximation, which selects a subset of columns and then try to represent the kernel as a projection on those columns. We can increase the cost of the construction of the preconditioner, but also create a better preconditioner by doing this whole idea, but doing the Nystrom idea in several steps. So we pick one column, and then we, in this incomplete Koleski approach, would then create a Nystrom approximation, then look at the Schur complement of this approximation to then have basically to project out this first dimension, and then we would go on and project out next dimensions, and this is more optimal and yields a better preconditioner because those directions would be guaranteed to be decorrelated. And then at the very extreme, this is in practice not feasible, we would do an eigendecomposition where we really just directly target the dominant spectrum and remove it, but obviously the cost of doing this is n to the power of 3, so this is as expensive as training the model itself. Now, one interesting observation is that we don't have to get too fancy with choosing the construction method for the preconditioner, because even for this is the spectrum of a kernel matrix for the aspirin molecule. So even for fairly small preconditioning sizes, those simple methods like Nystrom and the simplest method quickly performs the same way as the more expensive methods, namely the incomplete Koleski decomposition here. Obviously, the SVD will always be the best because that's the best thing you can do. So that's the lower bound here. But we can really rely on Nystrom approximation to construct this preconditioner. And even this step is not as is more subtle than it seems from the math. So here we would first construct the Nystrom approximation and then use the Woodbury identity to construct the inverse without instantiating, obviously, this full matrix. Now, doing this step is numerically has to be done in a numerically delicate way. And there's many tricks that we apply, but this is my favorite one. So one of the things is we have to take this inner part and then find the Koleski decomposition in order to, again, create the inverse, and we do this without actually doing this multiplication, because it squares the eigen or the singular values of the submatrix. We do it indirectly doing a so-called economical QR decomposition, and then the Q part of it is actually the Cholesky factor. So this is one of the tricks that we apply in order to form this inverse efficiently. And so so all of those tricks, we put them into our SGML force field, and then we applied them to this one test problem, for example, that I showed in the beginning. And then we see that, well, all of the atoms interact, and we get a good prediction accuracy. And then we can also use the efficiency of this approach to go to bigger systems. So here, for example, we have a double-walled nanotube that we trained, and then we used our model in long time scale and these simulations. And before there was no global model that could scale to those sizes. Okay, so.
Can I ask a quick question?
Yeah, sure.
So what you were just going through there was some of the work in the, like, I don't know if you're familiar with like GPyTorch and stuff that was doing similar linear algebra tricks in the, in a kind of machine learning community. I'm just curious how it compares. Like, did you try to, the developments they have, do they work for your systems, or did you?
Yeah, that's actually a good question. So GPyTorch introduces approximations, right? So they don't solve the full problem. They solve actually, so for them in this implementation, then the Nystrom approximation is actually already the solution, right? So, but here we only use the Nystrom as a preconditioner, but then we still converge to the full solution.
I mean, I thought that it has a lot of, bells and whistles, but I thought that you could just get like a normal, I thought it was pretty similar to the first part where you can do, conjugate your gradient and get basically exact solutions if you can configure it that way. And it scales pretty well. I mean, they have things where they try to fit on like, millions of points and things like that.
Yeah, but as far as I know, they don't, I mean, they essentially, so as far as I know, they essentially take this, they adopt a lowering approximation to the full matrix as the final model, right? So they're, because that gives you some computational benefits, obviously, that can be exploited. And here it's really just so all of the numerical tricks go into the construction of the preconditioner, and then we go from there. Okay, so the next topic is a little different, but it's also it's very much it comes from this data-driven perspective on the reconstruction problem, which is we saw many examples where we have different differential constraints that we impose on the models to make them to improve their inductive bias, and those differential constraints usually I think this is a phrase that I heard in one of Max Welling's talks somewhere. So he describes, he says that PDEs, they basically appear everywhere, almost every time a causal system interacts in some way, PDEs emerge. PDEs describe the system, they can be used to describe the system. And of course, obviously, as with any inductive bias, the benefit of introducing them into the model is that we can really only learn from a few examples and then generalize in a robust way, and we can trust those models more. In the force field modeling field, one of the this has been also popular, but one of the interesting things is that it's usually one constraint per paper, right? So people derive those constraints by hand, impose them onto the models, and it's so much work that they leave it at that, and then that creates the model. But then and then another problem is that if you impose such constraints, usually the model complexity increases tremendously, right? So, for example, if you impose a gradient constraint on a model, then you would have all the partial derivatives. And then suddenly, there's a factor that your model complexity increases by. Now, algorithmic differentiation promises to, or it can provide ways to overcome this, because it can exploit the tensor product structure of of complex differential constraints. So if we combine differential constraints in this in a linear way, then usually this product structure can be exploited by algorithmic differentiation to lower the complexity class when evaluating this constraint or this model, or this constraint on a particular point. And this can be exploited in Gaussian processes really nicely. For example, evaluating a Hessian vector product with algorithmic differentiation somewhat unintuitively is not quadratic in cost, but can be implemented with linear cost because it can be split into two operations. So two Jacobian vector operations that are executed one after the other, and that puts it in the linear complexity class versus the quadratic. So let me give you one example. So again, it's a Gaussian process. We impose some differential constraint here, and so in this example we want to create a Gaussian process that can learn from function value observations, from gradient observations, as well as Hessian observations. So if we combine all of those constraints into one model, we get a very complicated kernel, and this kernel contains all of the pairwise combinations of those constraints, which makes it very big. Now, those combinations of constraints luckily have this tensor product structure that can be exploited. And now with AD, we can actually, instead of fully instantiating those tensor products, we can evaluate them one after the other. So in this particular example, instead of when evaluating this kernel, instead of building the full matrix first and then applying it to a vector, we can express it as two multiplications that each scale linearly, and that obviously puts it in the linear complexity regime. Okay, so and this in practice this means that we can lower the cost by one order of magnitude for many differential constraints, right? So the full instantiation has this n factor, and then if we execute it one by the other, then we drop this n factor, one of those n factors for each of the constraints, and then therefore we have a more efficient constraint model. So, and the efficiency also somewhat unintuitively, the efficiency of the constraint model is the same as the same complexity class with a factor as the unconstrained model, right? So, for example, to relate this back to force field reconstruction, so a pure energy model is less complex than a model that has been trained in the gradient domain on forces, but using AD, we can still evaluate both models at the same linear complexity, right? And then empirically, we get what we expect. Okay, so this is one little example of how powerful those high-level constraints, differential constraints, can be. So here we in this test example, we reconstruct a two-dimensional Rosenberg function, and we try to reconstruct it from just 2 points, so 2 measurements. Those are the points that you see in white, and then this very faint white line is the reference function that we want to arrive at. And then obviously just by imposing just reconstructing this function from 2 function values is not enough, right? So we don't even get this minimum in the middle, right? But then if we add a derivative constraint at the same 2 points, then already the general structure of the function starts to emerge, and then we can go even further, again staying with those 2 points, but now we impose additional Hessian constraints on top, and we arrive at a very good approximation. And interestingly, with AD, we can impose those constraints without increasing the complexity class of the model. But the error, as you see in the corner, in the left corner here, reduces by 1 order of magnitude, right? So it's really quite effective to do it this way. And then here's another example. So this works for any, for most differential constraints. So here we solve the Laplace equation with boundary conditions. So here we have boundary conditions. that we impose, and again we use AD to do this in an efficient manner. Here's another example where we have another differential operator that we apply to the 1D wave equation, and again this can be done very efficiently and without any manual derivations, just using AD, and the results are obviously much improved versus really like just a function value based reconstruction. So inductive biases help.
For like the mean and the original kernel in that? Is it just like zero mean and?
Yeah, so in this case we just use the zero mean, yes. But in principle, if you have a good good prior for the mean, then this would also apply to the mean. Yeah.
And for the kernel, it's like some exponential squared smooth something for the kernel.
Yeah, this was just a regular Gaussian kernel. Yeah, without any. So just the Gaussian kernel only imposes a band limit on the reconstruction, and this is about the only assumption that it imposes, yeah. And all the other inductive biases really just came in those examples really just came from the differential constraint. Yeah. Okay, so the last example, I will be very brief here because I'm running out of time, but the last example is self-attention. So self-attention is an idea that's being widely used now, and I think everyone here is familiar with the general principle, but the idea is to take representations in the context of force field reconstruction, take representations of each of the atoms, and then we tokenize those representations in so-called query, key, and value vectors or representations. And then we let atoms interact by forming this inner product between the queries and the keys. And then if two atoms are similar according to this so-called attention value, then we propagate the value into the next layer, for example, right? So we pay attention to a particular interaction, or if they're not similar, we don't pay any attention. And the advantage of the self-attention mechanism is that we can really basically dynamically form those connections, right? So they're not learned once and then reapplied on every input, but here they're being formed depending on the input. And what's interesting is that those interactions, they don't always align with what you would expect from the chemistry or the physics, right? So certain interactions are stronger than, for example, what the bonding pattern would suggest. And they are really very much data-driven, right? So this is interesting because it, again, underscores that some complexity that we would expect from the physics is not present in the data-driven view. And then also the other way around, so some of the complexities, they only arise, if we look at this, at this problem as a statistical reconstruction problem, but they might be easy from a physics perspective, right? So we took the self-attention idea and created a geometrically aware transformer based on this idea. There's many of them out there now. And then we looked at we reconstruct force fields with this idea, and then we looked at the interactions that have been learned. And we found that those interactions, they're highly nonlinear, right? So they're not just simply reflecting the bonding pattern, for example, or simple pairwise interactions, but they're highly nonlinear and complex, and it really emerged from just from this attention idea. Okay, so one last thing I would like to advertise is our new data set. So a few years back, we introduced the MD17 dataset of small molecules with a few dozen atoms. And obviously, global interactions for those scales are not as important. So now we have an updated dataset that really presents global and non-local phenomena on a much bigger scale. So this set of problems scales up to a few hundred atoms. And if you're interested, if you want to play around with this data set, we'll invite you to go to our website and try them out. And we also have our models there that you can also try out. And and then build your own force fields. Thank you.